to in
Definitely.
order to get it right.
Yeah, that's why hopefully I try to get all those math questions out because I agree they were pretty tough. I was a more like master's grad school level stuff. That
I,
was
I guess it would have probably been all right if you were working with it every day,
Mhm.
but no.
Yeah, it was definitely. Well, thanks again. But yeah, if you finish, and that's for everyone else on here too. If you're finished, don't feel obligated to have to go on to these meetings. I can see when you're done with the course. And if you want to send me an email when you finish, or come on here like Courtney, you did, and tell me you're finished, just so I can update your grades. I
Yeah,
recommend that too, just for everyone on here, so you know, like, because I know for myself, like, I like to know what grade I'm gonna receive before I see it, like when it's permanent. I like to know, just in case there's ever mistakes or anything. So just send me an email when you finish, and I'll make sure that everything's updated on JetNet. And so again, I
yeah.
think this is out of 168 points. So you should see a score in JetNet out of that. And that score for now might not be your permanent score, depending on if you have more. Obviously, if you have more quizzes to still take, that grade will increase.
Right.
But okay, so
Hey,
unless go
yeah,
ahead.
so I'm free to leave then
Yep,
the meeting for tonight because I did actually already complete everything.
yep,
So
of course, you are good to go.
all right, great. You have a good weekend and stuff.
Thank you, you as well.
All right, thank you.
And to answer that question, there are 14 quizzes, I believe. I can look back and see and count them. There might be 13. I might have not counted right, but I sent you a chart in your emails, which I can pull up after this, and it'll show you if you count like the things. It'll say how many quizzes you have. For today, I'm going to kind of go over chapter 13 and 14. So that is quiz 13 and 14. Quiz 13 was the one that was over tidal energy. So don't get confused with what we talked about last weekend. So last weekend, or not last week, Thanksgiving, the week before that, we talked about wave energy. So tidal energy is similar, but it is different. So that's what chapter 13 is about. And then we are going to talk about chapter 14, which talks about thermal and salinity gradients. Before I get started, does anyone have any questions? Just to make sure there's no one waiting to ask any questions. No questions? Okay, we will get started then. Okay, so to kind of start off here first, so what is tidal energy at the most basic level? So essentially we know tides, like looking at this picture up here, you can see a high tide and a low tide. The high tide is the area where the water is, on more of the surface, and then the low tide is when it draws back out to the ocean. So we know from looking at past alternative energies that any type of motion, right, is kind of what all alternative energies, like how we harness them, right? Because any that's like wind energy is the wind moving, because essentially we can harness that motion to create mechanical energy, which is using a turbine or something to easily create and generate and create electricity. Okay, so before we get started, this is just a quick 3-minute video. I like to start here just so tidal power. This one is going to just kind of run through tidal power in the 3 different ways. Tell me if you can't see this YouTube video up. I think you should be able to see it, but I'm gonna just kind of run through the 3 different ways that we use or that we harness tidal power energy.
Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth.
And I'll talk about that a little bit more later on, about the role that the moon plays in tides and in energy in general.
Plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines.
So you'll notice too that these 3 sources of tidal energies are the ones that are covered in the book. So this is a pretty standard way of thinking about tidal energy.
Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity.
So I'm gonna pause there really quick too, so you can see that picture in the left corner there. And I think that is really interesting because if you've got anything out of the past couple of weeks, a lot of these alternative energy forms are using the same principles. Like I just mentioned, motion is a typical principle because it's kinetic energy and we can convert that. But looking at that tidal barrage, essentially what they're doing there is it's almost like a hydroelectric dam that we talked about a couple of weeks ago, right? That where you had an area that was at a higher point of water, so they dammed like a higher elevation point, and then when they released all that water fell because of gravity, and then made a turbine spin. So it's kind of a similar situation here. They're just utilizing a natural situation. So the benefit of that tidal barrage over a hydroelectric dam is you're not in that like similar picture right there. It's not essentially or I guess I would say the benefit, but the similar thing is you're having a barrier that's keeping the water. And when you release that barrier, that water is going down. So again, just a similar situation there, but it's utilizing something more that's a natural situation that happens. We're not, changing the environment in that sense.
Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far, the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity, and therefore do not provide sufficient capacity to satisfy demand.
I think that was a question on the tidal energy quiz if you haven't taken it yet. So it was that idea right there that it doesn't always create consistent electricity because you're not always getting the same amount of water that's, like the barrage, like entering the area.
That's tidal power.
So I'm going to go back to the PowerPoint. Hopefully it switched. I think when I switch over, I'm hoping, okay, it should have gone back there. Hopefully, if it didn't, if you don't see the PowerPoint, let me know in the chat. But okay, hopefully that was a good introduction of how tidal energy is working. Again, I'm going to stress this point because it is very, very important. You'll see at the end there that they still had a turbine, right? The turbine was moving and that was generating electricity. That is the key to all this alternate energy. All of these sources, eventually what the intent is to get a turbine moving either by motion, by gravitational force or something. Get that turbine moving because that mechanical motion of the turbine moving is what can create electrical energy, and electrical energy we can harness to create electricity. So just bringing that up again. So a couple of things about tidal energy, some more key points I want to talk about. So, it's produced during the rise and fall of the ocean water, right? The tides. It's similar to wave energy in the sense that it's harnessing the movement of the ocean. However, it is more predictable. So they talked about the fact that we know, like it's like the time frame for when there's a high tide or a low tide is very much known and can easily be found. So that's why it is more predictable than wave energy. Yeah. Question?
I just want to say when it was talking about tide, it is a very interesting thing. If you go up just north of Maine, there's the highest and lowest tide, and that's where it actually, as I showed with the globe, with the water gain larger, and then it moved to the sides. How the moon was going around it. the highest and lowest tide, it's the most craziest thing. It's like 3-4 stories tall, maybe higher, and then within 3-4 hours or more, it's completely drained all the way to, like, you could see the very bottom of it, and it's crazy.
Oh, wow. Huh, that is, you said in Maine?
It's in Canada, but it's just a little bit north of Maine. It's called
Okay.
like Biscayne or something.
Interesting. You know, I think that'd be a really good thing to look into. So I'll talk a little bit about that kind of later, or in the next slide, actually, about the role the moon plays. And in certain locations around the world, because of like the location that area is on Earth, it creates larger tide, like a larger difference in the low and high tide. So I'd be curious to like if we, I don't know on the top of my head, but if we looked it up, you could probably find a reasoning for why that specific area has that big of a difference in the tide. But that is really interesting. Okay, so let's see what else we got here. So, oh, one thing I do want to talk about. So, one of the big concerns with tidal energy, and the reason that it's a specific issue in the US is because of legal issues. And what I mean by that is no one owns the coastals mostly. And so you can't really like have a company go and create this whole plant because you can't really access that big of an area. So there are a lot of legal issues in terms of ownership there. Also environmental issues in the sense that creating that barrage, like the tidal barrage that we saw in that video, in order for like we talked about in that video how tidal energy isn't really used yet because of the fact that, oh yeah, go ahead, another question.
My biggest concern would be how could it affect could it mess up the way that the tide comes in and out? Could it, just like harm fish and animals and stuff that are moving in and out of the tide?
Definitely, because especially like the barrage, it'll block them. You're totally right there. It'll block all of the fish and animals in that area, which is a huge concern. So yeah, definitely. This is another one where like talking about tidal energy, if you don't really look into it and you just think, oh yeah, they're creating energy and then everyone thinks it's good, but there's a lot of negative impacts that this can have as well. And that's kind of why one of the reasons that it isn't used on wide scale applications. Okay, so the other thing I want to point out here, and I'll show an image in a second, but so water on the side of the earth facing the moon is more strongly attracted to the moon than water on the other side of the earth. And that has a big thing to do with tides and the reason that we have this varying motion. So I'm going to just kind of go into the next slide. So basically, what is the moon's role in this? And this picture here is really interesting. And I think after I'll explain it, this picture will make sense. But so basically, the moon has a gravitational pull, which creates something called a tidal force. And that force is essentially what's causing the water on Earth to bulge on the side closest and farthest to the moon. And this bulge is when there is a high tide. So in this situation here, you can see that this gravitational pull is causing Earth to bulge on the sides basically closest to the moon and farthest from the moon. And I'll explain that in a minute. And that's what this light blue is showing. It's just kind of showing that because of that pull or that tidal force, that's what's causing the high tides. And then obviously, since the Earth is rotating, that the areas of the low tide is when it's rotating and those areas are not either closest and farthest or somewhere in the middle. So and to kind of explain why the farthest side is affected, so that's because gravitational force is something called a differential force. So essentially what that means is basically the average gravitational pull force, or where it's, at the most typical time, is somewhere approximately in the center of the Earth. And a differential force means that when there's the greatest difference between the average and whatever it is at a given time, that's when it's going to be biggest. So differential just means a differential force is biggest when the difference is greater. So if we know that the average gravitational pull force is in the center, that makes sense as to why the sides closest and farthest to the moon are going to be affected. And that also explains why we have 2 high tides a day, because our Earth is rotating, and at one point you're going to be closest and at one point you're going to be farthest. So I think that's a really interesting picture. And to kind of explain it further, I love this diagram. So this is showing again, like kind of where it's pulling, again, because it's a gravitational force that's creating this bulge. Okay, so to kind of run into the barrage systems a little bit more, they talked about it in the video, so I won't touch on it too much. But basically, you know, I mentioned it's similar to a dam in the sense that we're dealing with water moving through a turbine to harness the electricity, and we're also dealing with the difference, right? Like the head loss, I guess you could say, if we have a area of low water and an area of high water, and we're harnessing gravity to essentially use this. So how a barrage system works is during periods of high tides, there's something called the sluice gates, which you can see right here. And those gates are going to open, and since they're opening and it's a high tide, we have water flowing into that. And then when they shut it, you know, somewhere in the middle, then they can open it again and all that water flows out. And that's what essentially spins the turbine. So the output of the turbine depends on the head of water. So what that means when you ever hear the term head of water, it's essentially just a height difference. So what it's saying is that the greater head or the greater height distance or depth of water you have on that side of your barrage, when you open that gate, you're going to have more water flowing in, which is going to make the turbine spin more, which ultimately is going to generate more electricity. So that's what that is saying. And that also goes back to the point that, you know, we don't always, the reason tidal power is kind of difficult is because we don't always create the same amount of electricity, even though our tidal waves are predictable, because we're not always getting the same influx of water. Okay, so this is just kind of showing how tidal lagoons work. And this diagram is in the book, but I shotted it into here because I think it's kind of interesting, just to kind of see how it's working. So in this first diagram here, we have the water is essentially even, I guess you could say. So we have that gate closed. And then the gate is going to block in this area when the tide changes, and then it's going to block essentially to keep all of this high water in. And then it's going to open, and when it opens, that high water is going to, you know, move right here. It's move all this water. Once this gate opens, all this water is going to move out here. Hopefully you can see my mouse. And that once that water moves out, it's going to spin that turbine. And then all of the water now is on this side in image D. So that's when they shut the gate again and then open it. And when they open it, all of the water flows back into the side, like you can see in E. And then it's the same process all over again. So it's essentially this process of using that gate to harness when the difference is the highest to shut it or close it, and then shut it or close it to essentially reverse the process all over again. So the benefit of this is because unlike a barrage system that only works one way, this tidal lagoon is working both ways, because it doesn't matter, you know, like you don't have to enclose a certain area because you can harness this turbine moving on both sides. You can kind of see like at this point, the highest side is in the middle, but at this point, the highest side is to the right. And so opening and closing that gate, that turbine is spinning both ways. The difference, going back to the lagoon, is when the lagoon is at the lowest point, this turbine doesn't spin. It only spins when you're releasing all that water from the basin. So that's just a difference between the two. So I want to talk about this question because it's kind of a math question, and I'm giving you the answer, I guess. But essentially, just kind of touch about this. So which of the following is not a true statement about underwater turbines as a mean of utilizing tidal energy? So let's kind of work through this. So 4 of them are true, right? So the turbine is used to drive a generator to produce electricity. Okay, we know that's true by both of these examples. We have our turbine, it's moving, and that's essentially generating electricity. So they make use of the kinetic energy associated with tidal currents. Kinetic energy, energy in motion. Obviously, in these situations, we're talking about gravitational differences, and that gravity is flowing the water down, but it's also a concept of kinetic energy because that water is moving. So we know that is true. This equation, you know, you might not know that, so we'll skip that one for now. I'll talk about it in a minute. This is just straight from the book, so it's pretty straightforward. I think it's 0.3 and 0.4. So you could see in the book, wherever they talk about coefficient of performance, you'll see that it doesn't say these numbers. And then the basic design follows along the lines of the design of a wind turbine. Again, this is kind of where this question's hard. Like there's a some people that you could probably justify the answer by saying, no, it's clearly a lot different because of obviously you're going to have different components, different chemicals and materials and processes to create wind turbine and create, a tidal turbine, I guess you would say. So that one's kind of difficult, but the easiest giveaway here is this typical coefficient. That's wrong, but going back to C, so the reason that this equation is true, so in the book, they give you this equation on the right here, and you can see that it's pretty similar. The only difference is this says P over A, and this one has an A in it. So all they did here is just move this A to this side, and anytime you have a fraction in an equation that has an equal sign, you can move it to the other side by, we can move whatever's in the denominator to the other side by multiplying. So if we basically put times A on this P over A side, and whatever you do to one side, you have to do the other. So you put A here, and then this A cancels. So essentially, this P over A equals 1/2 C BV cubed. It's the same thing as this. They just used algebra to put this A over to this side. So yes, this one is true. The power generated can be calculated from this equation, but you won't have to do any math for that equation. But essentially, all of this was to just tell you that this is the answer T. And you don't have to do any math there, but I just wanted to kind of show you that that really wasn't like a difficult, it wasn't too bad of a math problem. Okay, so I want to talk about this for a minute too, because I think it's an interesting point. So the ocean has energy because of waves and tides. And this is a quiz concept. And this was one actually on the quiz. I was kind of looking at some of the questions they were asking, and I struggled on this for a minute because I'm like, okay, I think it asks the ocean has energy because of waves and blank. And I wanted to say because of waves and wind, because it just made sense in my mind. And then I thought about it a little bit more. So the answer is because of waves and tides. And we know that because we utilize the idea or the concept of waves to create energy, just like we utilize the idea and the concept of tides to create energy. And we also know that waves are driven by winds. So winds aren't causing energy, but the waves are. And likewise, tides are driven by gravitational pull of Earth. So that is why the answer here isn't winds. And that's also why it isn't the gravitational pull. So the answer is waves and tides, because those are like legitimately what is the reasoning for why we have energy. Okay. So the potential generator, oh, I like this question. Another math question that really isn't too bad if you look at it. So the potential energy available from tidal movement is, and then they give this weird equation that you don't need to know why to use that. But from this, determine what the average power, I think that's supposed to say, available over a tidal period T will be. Okay, so we can look at all these answer choices and we can see that, so this one's the same equation. This little caret here, or this little like upside down triangle, it just means that it's squared up top. So why they didn't put it up top here, I don't know. But same thing here. This one is just this whole equation times T, which is the tidal period. This whole equation has some weird, they're T to the cubed. And then this equation is divided by T. So just using, like, I guess you really don't have to use math here, but we know that over a tidal period. So when something's over a period, it's over a period of time. And over means divided by. So the answer here is D, because we want to know the potential energy over a period of time. So we divide it by T. Just for example, let's say that this tidal period was 10 days. And we wanted to know the energy, the average energy each day per the 10 days. So the way that we figure that out is we use this equation and calculate the total potential energy over that 10 days. And then we divide it by 10 to figure out the daily potential energy. So that's just why the answer here is T. And again, it's just because you always divide by a period. So I wanted to show this answer because again, it looks like it's a theory math problem, but it really isn't. Okay, so moving on, but I think this was, yeah, let's talk about this question first. So this is another question that I wanted to bring up solely because if you aren't completely accurate with your calculations, it gives you a wrong answer. So I think the question asks from 1995 to 2010, what is the percentage increase of, and this is cumulative capacity, so power basically, in 3 different areas. And we talked about this graph last week, how basically it color coordinates to like different categories. So in this situation, it's different locations, but you get the benefit of this graph is you can kind of visualize like the total, and you can also visualize usage for particular locations. So in this situation, again, it was asking for the percentage increase from 1995 to 2010. And we can see that, right, it's a significant increase. So the way that you do this equation, or the math here, is that in 1995, we can see, and again, this is kind of where estimations come into play, and you can easily get the answer wrong if you're not completely accurate, which is frustrating. So at 1995, you can, if we kind of went all the way over here, it's at about 5. And originally when I did this, I was ballparking it, and I'm like, okay, it's at about 10. If you say 10, it's a totally different answer. So it's not 10. It is, the correct answer is about 5. So again, you find this by going here, we can see that it's all the way, this is where the line stops. I'm using the yellow line, or this line and not this line, because we're looking at the total percentage increase, not just in one location. So this is at 5. And then if you went to 2010, this kind of cuts it off, it's at 100. So this is a formula here for the percentage increase, just equals 100 times the final minus the initial divided by the initial. Okay, so our final cumulative capacity was at 100, right? And because that's in 2010, and our initial was at 1995, which was 5. So in order to do this math, if you typed into your calculator or your phone, 100 minus 5, which is 95, and then you divide that by your initial, which was 5, you would get 19. However, 19%, if you look at this question, is not your answer, and that's because this equation requires you to multiply by 100. So 19 times 100 is 1900%. And maybe in like basic math classes, they might have talked about how percentages can never be above 100%, but when we're talking about percentage increase, it can be. So basically it's saying that from 1995 to 2010, it had a 1900% increase, a huge, which essentially the point of this was just saying that there's a significant demand, I guess, or usage of this over time. So I just wanted to talk about that question and talk about the math behind it, but you will see this when you are taking the quiz. So where were we? Okay, so last little bit here, I'll probably end a little bit early. So the other bit I wanted to talk about a little bit was chapter 14. And essentially what this chapter talks about is a whole new concept of alternative energy that you probably don't have any prior knowledge on, just because it is a really complicated one. However, the concepts behind it are something that are utilized in a lot of different areas of technology. So I'll talk about that in a second. But so this section is about ocean thermal energy conversion. So I missed a slide. Start here. This section is about harnessing energy from other ocean sources. So now we're not talking about waves, we're not talking about tidal energy, we're actually not really talking about motion, we're talking about gradients. So we're talking about thermal gradients and salinity gradients. So essentially what a gradient is it's just a change. So thermal means heat, so the change in temperature. Salinity means salt, so the change in salt levels. And gradients, salinity gradients are something that are used in a lot of different areas, like when talking about like cell osmosis and everything like that. And there's like a hypertonic and hypotonic solutions. I don't know if any of you take biology classes or for part of your degree, they talk a lot about hypertonic and hypotonic solutions, and all that's just related to like salinity gradients. So these ideas were something that like have been around, I guess, for a while, but we're actually now using them to harness electricity. Okay, so let's talk about the thermal energy side of it for a second here. Essentially what the thermal energy gradient is doing is it's harnessing the fact that we have different temperatures on the ocean's surface, or on the ocean's depth, I should say. So, and we all know this, right, from like swimming in the pool, like how that top layer on a really, really hot day is like warm, and then below it, the like deeper water is cold. And that's what this thermal gradient is. It's that we have that top layer of hot water, or I shouldn't say hot, but warmer water, and then, you know, like lower water, deeper, that is colder. So this chart I think is really interesting. What this chart is showing is that at increasing depths, it stays like after about 1,000 degrees, or 1,000 degrees, after about 1,000 meters, the depth of the ocean is pretty consistent at 4 degrees. However, the top of the ocean, so 1,000 meters and up, our ocean is varying a lot. So, you know, for example, it's saying at about 500, it might be like 12 degrees. At about 0, so right at the surface, it could be up to 22 degrees. So that is kind of highlighting this thermal gradient, and the fact that at the deeper weathers, or at the deeper depths, we had this really cold, consistent temperature, right? From 1,000 all the way to 4,500, it's staying at 4 degrees, but this top layer, the temperature is really increasing quite a bit. So that's, I guess, the idea behind ocean thermal energy. So what I'm going to talk about in a minute here is that there are 3 types of cycle systems that are used to create or generate electricity. That is called an open cycle system, closed cycle system, and a hybrid system. And in order to use these systems to generate electricity, we need this temperature gradient. So to kind of show diagrams that they show in the book, this is called an open cycle system. So essentially what this is doing is it's using seawater during heating and cooling periods. And then it also requires a very large turbine. So you can see this turbine here. So essentially what's happening here is the warm seawater on the top layer, right? We have this gradient, we have top in higher temperatures at the top. So it's using the warm seawater in here, and that's going to go through an evaporator, where then we're going to be left with water vapor, and that water vapor is used to spin a turbine. And then we know that that turbine is used to move a generator, which is going to create electricity. The downside of, or the like fall of this, means that then we have the water vapor going out into a condenser that's getting cooled by the cold seawater coming in right at the bottom of the ocean. And then this whole process can start again. So the reason this is called an open system is because we're it's open to the atmosphere, or I guess the environment, right? We're not using any other chemicals or anything. We're simply using and harnessing the idea behind, we have warm water and we have cold water, and we're going to use the warm water to create water vapor to move a turbine, and then we're going to use cold water to cool that water and then restart this whole process. So that's essentially what an open cycle system is, and how we are generating electricity by using that thermal gradient. A closed cycle system, pretty similar. You can see that the diagram actually looks just about the same. The only difference here is that, actually this might be the same diagram. Oh, no, it's not. Okay, you see this little line here, this liquid line. That's the only thing that's different. So in a closed cycle system, we're not just using seawater. We are using another type of fluid, which is called a working fluid. Which essentially serves the purpose of right here. You can see it. So the vaporized fluid is what is used to drive the turbine, essentially. So this vapor fluid here that's going into the evaporator is what's going into the turbine. And that warm seawater is still used, but it's essentially used to heat up the ammonia, typically, is what this liquid is. So that's the difference between a closed and an open system. Again, open is actually evaporating the water, whereas a closed system is evaporating something called a working fluid. And I believe the reason the closed system is used is because working fluids like ammonia have different boiling points, which means they are likely easier to vaporize and ultimately move the turbine. So that is why a closed system uses a different substance. But the other thing I want to talk about here is the negative of using a closed system is that there are environmental issues, and I'm sure you can imagine them. So ammonia, we don't really want a ton of ammonia in the water, especially in the fact that with anything time, I think I mentioned before, but I am a drinking water engineer. So anytime there's anything that could potentially get into the water, it is not a good thing because especially chemicals like ammonia that are like inorganic compounds. We do not want those in our water that we could potentially drink. So that's a huge environmental concern, not just for animals and plants and wildlife, but for us. If there's ever a leak that gets into the open water, then that is a significant issue. And I guess the argument here is, well, we don't drink the ocean water, right? But unfortunately, in Michigan, that's true. We use most of our water comes from ground or from the Great Lakes. But in other states, there's something called reverse osmosis that is a whole other story that actually uses this idea of a salinity gradient to get rid of the salt in water. And that's kind of what I was talking about earlier when I said there's different uses of this salinity and temperature gradient. So reverse osmosis is an example of using, essentially getting the salt out of the water so we can drink it. So yes, we do potentially drink ocean water. It's just an expensive and energy extensive process. But okay, back to this, just to again say that point, environmental issues clearly when we're using a certain type of liquid or chemical into the situation. So that's probably the most significant thing here. So hybrid cycle system, that's the third type of system. And essentially that's just using both seawater and another fluid as the working fluid. So the condenser is still cooled with seawater, but unlike an open system, only the vaporized fluid is running through the turbines. So in this situation, we've got the harnessing of both water vapors. Okay, so those are just the three types of systems. To kind of touch briefly on this, and this is actually my last point. So the implementation of OTEC systems, which again, OTC just stands for Ocean Thermal Energy Conversion Systems. We can either have one on shore, mounted to the ocean floor, or floating. And again, this is talking about these systems depending on whatever one hybrid, closed, or open we have. So when something, oh yeah.
I just wanted to ask you a quick question. What is your opinion on the hybrid between water and wind power turbines? It's a new thing that they're coming out with. It's basically they put them on a beach in a concrete box, basically. And when the waves crash into the walls, it pushes the wave up inside of it, which causes air to flow out through this thing, and it causes a fan to spin because of the wind being pushed out. And when the wave goes back down, it causes wind to come back in, causes it to turn again, make a motor or makes a generator make electricity.
That's interesting. I'll have to look into that. I don't know too much about it. I think my initial thoughts would be I would have questions about how big they are, right? Like, I don't know how much energy, I don't know the comparison between the energy you would create from wind moving a fan or waves moving a fan, essentially, right? And I wouldn't know how big that fan or that turbine moving would have to be. That would probably be my biggest question, because that's my biggest concern with wind energy. I think wind energy is probably in terms of consequences, probably has the least amount of consequences, right? Like we're not impacting like wildlife essentially, but my issue with wind energy is the creation of turbines, right? Because these turbines have to be big, they have to use a lot of materials, they have to be transported. So I'd be curious to see if the hybrid situations require a similar size. That would be my question. Do you know anything about that, how big they are?
I'm not too sure on how big they are. I believe they aren't like too extremely big. I believe they're about the size of, I think it's like 4 people standing shoulder to shoulder, and it's about I want to say it's about 6 foot tall. I can't remember exactly how big it was. It wasn't that big, and I was kind of worried.
Smaller than a wind one, so
Yeah, that's what my main problem was, is how can this produce a lot of energy, you know, for the size of it. My main problem for the windmills and stuff is that when they can't work after 25 years, since they're made out of fiberglass, they can't recycle them. They have to put them back into like the ground and whatnot. That's my biggest problem with windmills.
I'll actually have to, I meant to find that article for everyone to read. The turbine graveyard, they call it. I forget what state it's in, but there's a legitimate graveyard of all of the old turbines that have gone bad that they can't use anymore, and they don't, like you said, they don't know what to do with them. And that is a huge
Because you
concern.
can't recycle fiberglass. My second being that it kills a lot of birds. Surprisingly, I did not know that windmills killed the amount of birds they did.
Huh, I'd be curious on that too. I guess I don't know the answer to that. I knew it impacted birds, but I didn't know that it like was a significant amount. So
If I'm
that,
not mistaken, it's one of the biggest factors of birds and their
Huh.
lives because it messes up. It kills a lot of bats too because it messes up with their um
oh, they don't have good vision.
yeah.
Anyway, I can't see the. Huh. Yeah, that's really interesting. Thanks. Yeah, I'll have to look into the hybrid ones, because this book didn't talk about it, but I'd be curious to look into that more. So, real quick, last little bit here. So, implementation of these OTEC systems. So we either have them on shore, like really close to the water. So it's either like on land or like in very shallow water. So, and that's essentially where there's, good thermal gradient. The negatives for this is when we're building it onshore, we have a lot of upfront costs, right? Like, because we have to build some sort of structure similar to these onshore. Positive to this, and a really interesting one, is that this process here of like evaporating and condensing the water, essentially that condensed water loses its salt. So going back to this, that condensed water becomes fresh water, and that is a suitable drinking water source. So that's really, really interesting, and especially interesting because I mentioned that it is expensive to use reverse osmosis at drinking water plants to get rid of the salt in water, but this is kind of killing two birds in one stone, right? Because it's creating energy and creating fresh water, which requires a lot of energy. So it's interesting. So I think the one question I would have here, and the book doesn't talk about it, but going back to the closed cycle and a hybrid system, we're using another fluid. And is there potential for that fluid to get into that finished water that we'd potentially treat? Because that'd be a big concern for me, because some of the other working fluids they use besides ammonia is like Freon, which is definitely not something that we want in our drinking water. So that would be a question I have there, but that's just kind of a point for that one. And the other two, it can be mounted on the ocean floor, so like somewhere on the continental shelf, so pretty deep in the ocean, which probably has a lot of upfront costs too, just getting it down that deep. And then we can also have it floating, which is probably the cheapest and easiest way. But I don't really know. I don't know if the book touches too much on the concerns there with having it floating, but I imagine maybe it could impact birds and everything there, right, that float on the shore or on the top layer of the water. But yeah, so, and then this is just, that I already talked about. So that's all I had for today. So hopefully that was interesting, helpful, something. And then, so this was again, chapter 13 and 14. I'll probably talk about 15 and 16 next week. And then the following week is our last week. So you have just a couple more weeks to get these last couple quizzes done. But this, hopefully, I tried to touch on quite a few of the answers or questions they ask. I didn't touch too much on the salinity side. So, but it's, the book has like one page about the salinity gradient. So this was all about, right, the thermal gradients we were using. So definitely read that. But it's pretty straightforward, and a lot of the questions they ask on the salinity gradient are like straight, like textbook. You can easily find the answers. But if you have questions about them, just send me an email and let me know. But for now, that is all I have.